This is the machine that almost half of all Americans interact with at least once a week, and almost no one actually understands how it works. Every time you pull into a gas station, lift that handle and hear that click when your tank is full. An entire system of physics, engineering, and regulation is operating beneath your feet and inside that nozzle. Here's exactly how it all works. Let's start at the beginning, literally underground. Beneath every gas station, there are 2 or 3 large tanks buried in the earth, each one capable of holding several thousand gallons of gasoline. These tanks are connected by underground piping to the dispensers you see above ground. And here's the first problem the system has to solve. The fuel is down there, and you need it up here. Gasoline has to defy gravity to reach your car. To do that, most gas stations in North America use what's called a submersible turbine pump, a pump that is physically submerged inside the underground storage tank. It uses a propeller-like device called an impeller to push fuel upward through the piping and into the dispenser. Other systems use a suction pump, which works differently. A motor above the fuel level removes air from a pipe inserted into the tank, lowering the air pressure above the gasoline. When that air pressure drops low enough, the gas climbs up on its own. In technical terms, what you see at the gas station is not actually a gas pump. It's a fuel dispenser. The actual pumping happens underground. That distinction matters more than most people realize. Once fuel reaches the dispenser, it enters a machine with 2 distinct halves working in tandem. The first is the electronic head, an embedded computer that controls the pump's operation, drives the display, and communicates with the sales system inside. Modern pump displays can actually run variations of operating systems, and some can display advertisements or carry on simple interactions with customers. The second half is the mechanical section, a motor, a pumping unit, valves, and most importantly, a flow meter. The flow meter measures exactly how much fuel is dispensed. In older pumps, that meter was physically connected to real numerical displays, the spinning number wheels you may remember. In modern pumps, the meter converts its movement into electronic pulses using a rotary encoder, and those pulses become the numbers on the screen. When you select a grade and lift the handle, a switch activates the flow. Fuel travels from the underground tank, through the piping, through the flow meter, and down the hose to the nozzle in your hand. Here is where the system gets genuinely remarkable, and where most people assume there must be some kind of electronic sensor doing the work. There isn't. The mechanism that stops your gas pump automatically when your tank is full is entirely mechanical. It uses physics discovered by an Italian physicist named Giovanni Venturi in 1797. Here's how it works. Running alongside the nozzle spout is a small tube, and near the tip of the nozzle, there is a tiny hole. As long as your tank isn't full, air flows freely through that hole and through the tube. Inside the nozzle handle, the flowing air passes through a constriction in the tube, a Venturi tube, which speeds the air up, which drops the pressure. That drop in pressure holds a mechanical valve open, and the gas keeps flowing. But the moment the rising fuel in your tank covers that small hole at the nozzle tip, the airflow stops. The pressure in the Venturi tube changes. A mechanical linkage in the handle detects that pressure shift and releases the valve, which is spring-loaded, and the trigger snaps back. The pump shuts off. No electronics, no camera, no computer sensor, just a hole, a tube, and physics that are over 200 years old. The nozzle also has one additional safety feature worth knowing about: a breakaway valve in the hose. If you ever drive away from the pump with the nozzle still in your tank, this valve causes the hose to detach automatically, stopping fuel flow immediately. You've probably noticed the pump offers you choices: regular, mid-grade, and premium. These grades are defined by their octane rating, displayed as a number on the yellow sticker on every pump. Octane is a measure of fuel stability. Specifically, it measures how well the fuel resists detonating too early inside your engine cylinder. When fuel ignites before the spark plug fires, called engine knock, it creates uncontrolled pressure spikes that can damage your engine. Higher octane fuel is more resistant to that early ignition. In the United States, regular gasoline is typically 87 octane. Mid-grade is usually 89. Premium is generally 91 to 93 depending on location. The octane number is actually an average of 2 separate laboratory tests: the research octane rating and the motor octane rating. which is what the R plus M over 2 label on the pump refers to. It's also worth noting that more than 98% of U.S. gasoline contains ethanol. Most standard gasoline is 90% petroleum and 10% ethanol. The ethanol serves a dual purpose. It provides a significant octane boost to the petroleum, and it satisfies federal renewable fuel requirements. Some stations also offer E85, a blend of 85% ethanol and only 15% petroleum, which is intended exclusively for flex fuel vehicles. Some pumps don't even carry separate tanks for each grade. In some systems, the pump blends a high-octane fuel and a low-octane fuel in precise ratios to produce the mid-grade right at the dispenser. This lets retailers stock only 2 tanks but offer 3 products, saving storage space and working capital. There's one more system operating every time you fuel up, one that is nearly invisible but critically important. Gasoline vapor. When fuel fills your tank, it displaces vapors already sitting above the fuel. Those vapors contain volatile organic compounds, including benzene and toluene, that react with sunlight and heat to form ground-level ozone, commonly known as smog. For decades, those vapors simply vented into the air around you. Today, gas stations use vapor recovery systems designed to capture those emissions at 2 stages. Stage 1 happens when a delivery tanker refills the underground tanks. As fuel flows in, the vapors displaced from the underground tank travel back up into the tanker through a dedicated return line and are eventually recovered or destroyed at the distribution terminal. Stage 2 happens when you fuel up. Some nozzles have a rubber boot or bellows that forms a seal around your car's fuel inlet. As gasoline enters your tank and pushes vapors out, those vapors are captured through ports in the nozzle and routed back down through the hose and into the underground storage tank, instead of into the atmosphere. More advanced systems use a vacuum pump in the dispenser to actively pull those vapors back, capturing up to 95% of what would otherwise be released. As of the late 1990s and into the 2000s, car manufacturers were required to build onboard vapor recovery systems directly into vehicles. Because modern cars recapture vapors themselves, most states outside of California have now allowed the station-side Stage 2 systems to be phased out, since the cars themselves are doing the work. None of this happened overnight. The entire system you interact with today traces back to a single transaction on September 5, 1885. When an inventor named Sylvanus Freelove Bowser sold a kerosene pump to a grocery store owner named Jake Gumper in Fort Wayne, Indiana.